Okay, hello everyone, I'm Shen. So I made this video to just briefly introduce how we actually use the code to control the motion of the hexapod robot. Okay, so currently we are using a code called NUKE, which stands for Nearly Universal Kinematics Engine. This code is kind of like, I think it's already pretty old, and you can find the information from this RTBox robot controller here. Just type the name and you will find like some information stuff. Okay, but the version we are currently using, it comes from a Phantom X hexapod robot we actually bought a few years ago. Okay, so so it's open source, so we just get the code and then we modify it, put it into that view and make it work. But then it's like pretty old, and also like there are bugs, and I get a lot of complaint about like the coding style is not very good. So I have some goals in my mind, like we can just use Python to write write a new version by ourselves. Okay, so I made this video just get you guys an idea how the current code actually works. Okay, so I separate the video into several pieces, just make it like more flexible. And then this piece of video, I'm going to give some basic idea of like what's the like background knowledge, and then the definition, some basic notion stuff. Okay, so the node code, basically it has like 5 most important files. There's a main file, there's a gate.h file, there's a nuke.h file, there's a bioloid controller CPP along with a .h file. Okay, so this main file, which is like, as you see, it's called a hexapod dynamics 106 5.0 right now. It works as a main. It does the process flow of like getting the command from like human controller or like a computer, like just like getting a command, and then you generate the gate, and then you solve the body IK, leg IK, and then you do the interpolation. So it has the complete like process flow. Okay, so I'm going to explain those things a little bit better if you haven't taken any courses on like kinematics of robotics. Okay, then you have this gate.h file here, which is basically the gate generator. So it generates the gate. It tells like the robot when I should put like which leg on the ground, when I should like pick which leg on the air. Okay, so this is a gate.h file, and then this bioloid.cpp as long as bioloid.h. Those two things serve as a interpolation. Okay, again I'm going to explain this more in detail. And this nuke.h is just a definition of like the leg configuration, and you will be able to find how many legs you have. Obviously you have 6, and then you have like the size of your body, the size of your leg, whatever, like the ID of your leg, whatever stuff. Okay, so those are the main files we're going to use. We are currently using in the code. Okay, so I will briefly introduce like the basic notions of the robot kinematics. So if you already took Dr. Hong's class 263A, so you should be able to, you should know all those stuff. And if you haven't take that class, and you happen to be very free, okay, which doesn't happen too much, so there's actually an online version. So you can go to YouTube and just type an introduction to robotics, Stanford Osama Khatib. He actually teach a class, and then I think the first few lectures is going to teach those basic stuff of the robot forward kinematics, inverse kinematics. Okay, so you can watch them and you will have you will have like same details of like the Dr. Holmes class. Okay, so we have the robot. So we have a hexapod robot. Okay, so hexapod robot has a hexagon as its body, and then we have a leg. So let's say we have a one leg like this. Okay, so this is a hexapod robot. Okay, so usually we call the toe, we call like if you have a leg or you have a hand, and then we call like the end point which actually touches on the physical world, we call it end effector. Okay, so this is just one term we usually use. And then okay, so in order to generate like a motion, we need the mathematical model to describe like how the robot actually like move, right? So the usually way we do it is by attach frame to the robot body and the leg or the limb. Okay, so the current code has this definition of like the z-axis, x-axis, and y-axis. Okay, so it's just a very normal, very usual definition of the coordinate system. And then this coordinate system is attached to the robot body. So this actually is a body coordinate system, and it moves along with the body. So if you have a world coordinate system, which is fixed relative to the world, and then the relative motion of the robot body with respect to the world can be described by the transformation of like two different frames, two different coordinate systems. Okay, so the same idea applies. So when we attach the coordinate system to the leg. So in this OneNote documentation, I have a hexapod DH parameters here. So you will be able to see the one hexapod leg with like different coordinate systems attached to the leg. Okay, so the hexapod leg we currently using has a 3 degree of freedom, which means there's a 3 joint. Okay, so like you can see one joint here, one joint here, and also one joint here. Those are the motors it actually moves. Okay, so as you can see, like one motion you need a one coordinate system, right? So there's a base coordinate system xyz 0, and there's xyz 1, and the xyz 2, and the xyz 3. Okay, so those describe like the motion of each section of the leg. And then you have a end effector here which has its own coordinate system. Okay, so by writing down the coordinate system, we can define what's called the DH parameters, and which actually describe like the relative motion of the coordinate system, relative transformation of the coordinate system, and we can actually make those things into the transformation matrices, which I actually put here. Okay, so this is like the usual way we describe a robot motion. Okay, so you have an end effector and you attach frames, and you do the frame transformation. That will give you the like a kinematics description, a mathematical description of how a robot will move. And then I'm going to briefly introduce what is forward kinematics, which usually say FK, and what's the inverse kinematics, which is usually say we usually short for IK. Okay, so you have a, say you have a leg, okay, and then as we see, you have a different motors. And then there's an end effector here. Okay, so forward kinematics is basically given the rotation angle of the motors. So if I know this motor 1, what's the position of like rotational position of motor 1, and what's the rotational position of motor 2, and this Fk will give you the position of the end effector. Okay, so from those, say this is theta 1 and this is theta 2. Okay, the end effector position you can describe by x, y, z, a vector, and then Fk will just give you x, y, z as a function of the theta 1 and theta 2. Okay, this is Fk, and the Ik is basically given. So usually what the problem we actually cares is like, I want to put my hand, say I want to put my hand on the table, and then the motors are actually like the actuators. So what we can actually drive is the motors. Okay, so we know we are given a task of putting like a hand on the table. So what is the motor angles we need to drive at? Okay, so you can see it's just an inverse function of this Fk, right? So Ik is I'm given the target x, y, z. Okay, let's put G here. So I want to solve for my rotational angle of motors theta 1 and theta 2. Okay, this is Ik, this is Fk, this is Ik. Okay, so as you can see, basically Fk and Ik, it construct the correlation of like the driving part, which is the motors, and also the tasking, like the end effector, which is actually performing the task on the physical environment. Okay, so this is Fk, Ik, and then after we finish Fk and Ik, we already have the relation. And then how to, so say right now I say I want to put my hand on the table, and then my hand is right now, it's on the air. Okay, so for each point I know where should I drive my motors, but then how should I actually perform a trajectory to move from my current hand position on the air to the table, to the position on the table. So there's going to be a trajectory generation here to tell me how actually how should I actually move, right? So this is a trajectory generation problem, and then which basically is you need to generate a sequence of like either theta, so trajectory, okay, so you need to generate a sequence of x, so generate a sequence of x, y, z, say, and a sequence of theta 1 and theta 2 to perform the task of like putting my hand on air, and then you go all the way boom to like the hand on the table. Okay, this is a trajectory. Boom, boom, boom. Okay, so as you can see, if you have a Fk and Ik, then you given one of them, you generate one trajectory either in the xyz space or in the joint space, which is like theta space. So you can have the other, right? So there are actually two ways to do this task. Either you can do it in the xyz space, or you can do it in the theta space. And then the current code we are using on the hexapod NUKE code, it does it in the theta space. Okay, so what actually happening is you have a you set the like key points of like your theta, and then you actually like interpolate. So you have a okay. So you actually generate the trajectory in the theta space. So what's actually going on is you set the key points of like the where you want to go on the actual XYZ space, and then you use your IK. Okay, so you have an IK here, you transform these key points. So this is like key points. This is 1, 2, 3. Okay, so you transform these key points into your theta space. So you have a theta space key points theta 1, theta 2, key points theta 3. Okay, and then you do the interpolation. So you have a points, right? So you can actually interpolate, and you have like a sequence of theta between those key points, and that's how it actually does the trajectory generation. Okay, so after you do the trajectory generation, you need to generate a gate. Okay, so I should say this. So the trajectory generation is one layer like lower, and one higher layer is like how you actually generate the gate. So gate generation, it tells like the robot which leg I actually needs to pick up, right? So the hexapod right now has like 3 different gates. So one of them actually pick up like 1 foot at a time, which is called a ripple, and then the second one picks like 2 foot up of like once, so that's called the amble. And then the tripod gate, the third kind of gate, picks up like 3 legs once. Okay, so you need to have like such an information of when you should pick up legs. Okay, so let's say the gate engine tells you, okay, this leg, this which is let's say it's leg 1, and then right now you need to pick up leg 1. Okay, so you pick up leg 1 like this step, you just pick it on the air. Okay, so let's say this is step 1, this is step 2. Okay, so from step 1 to step 2, you pick up 1 leg. If you pick up leg 1, and then you actually use your trajectory generation to generate the sequence of these, and of course it happens in the theta space. Okay, and then so you generate a sequence of this picking up motion, and that's how it actually moves. Okay, so as you can see, the whole thing kind of works like you first generate the gate, and then you call trajectory generation, and then in order to generate trajectory, you need to have like IK or FK. Okay, so this thing is like a layer 1, layer 2, layer 3, kind of like that. Okay, that's pretty much the background information. And then the next section, I'm going to look into details of like how each part works, especially the gate engine. Okay, so thanks.